So now we know what multicollinearity is and what are the potential sources of it. Now let's discuss the practical consequences of multicollinearity. Even though the OLS estimators are still unbiased, consistent, and efficient, they have large variances and covariances, which makes precise estimation very difficult. So in other words, even though the OLS estimators still possess their normality properties, because of large variances and covariances, it is very difficult to have precise estimates. So your estimates will be actually not the way they should be. And because of this, the confidence intervals tend to be much wider, so they're much bigger, leading to the acceptance of the zero null hypothesis. So in a sense, because of multicollinearity, our confidence intervals are wider, which means that we cannot reject the null hypothesis. So we have to accept the null hypothesis, even though maybe if there was no multicollinearity present in our data, we would have rejected the null hypothesis. So the presence of multicollinearity makes us accept the null hypothesis, even though it might happen that it shouldn't be accepted. Also, because of large variances and covariances, the t ratios of our coefficients tend to be statistically insignificant. So indicating that our coefficients are statistically insignificant, even though they should be statistically significant. Even though the t ratios will be statistically insignificant, the coefficient of determination, or r squared, which is the overall measure of goodness of fit, can be very high. And this is actually one of the ways multicollinearity can be detected. I will come back to it later during the detection section. But from this property, you already know that if you have statistically insignificant t ratios but a very high coefficient of determination, that means that most probably you have multicollinearity in your data. Besides, the OLS estimators and their standard errors can be sensitive to small changes in the data. So let's assume you have one set of data, you estimate your model, you get very nice results, but the moment you add, let's say, even 2 extra observations, you might get completely different results, maybe statistically insignificant. And this is what multicollinearity does to our data set. It makes it very sensitive to the changes in the data. Let's have a look at some illustrative example. So here we've got the regression results of consumption on X2, which is income, and X3, which is wealth. So if you look at the t statistics, you will see that in case of the slope coefficients, they are lower than 2, indicating that both coefficients are statistically insignificant. So they are not statistically different from 0. However, if you look at the coefficient of determination, you will see that it is very high. It's actually very close to 1. So on one hand, we have statistically insignificant coefficients, meaning that X2 and X3 do not explain y. But on the other hand, we get the result that 96% of the variation in y is explained by X2 and X3, which is kind of a paradox. So this is what I've just said. Another interesting paradox is that if you test the hypothesis that beta 2 and beta 3, so the slope coefficients, are simultaneously equal to 0, this hypothesis will be rejected. And so if you look at this result, the F statistic is equal to 92, and you'll have to believe me, it is very, very much higher than the critical value. So we reject the null hypothesis that beta 2 and beta 3 are simultaneously equal to 0, which means that simultaneously they are different from 0. So you see, on one hand, we get that that individually those coefficients are statistically insignificant, right? And we know this from the t ratios right here. But on the other hand, we get that jointly the coefficients are statistically different from 0. Another paradox. So the conclusion that we can make based on these results, based on the result of the t statistics, of the r squared and f statistic, is that X2 and X3, the 2 explanatory variables, are highly correlated. Another way we can check is doing this. So we can regress actual X3 on X2. And if you look at the t ratio, you will see that The t-statistic is very high, much higher than 2, indicating that x2 is actually that x3 is actually a function of x2, confirming our previous conclusion about the correlation between the two variables. If you regress y on x2 only, you will also get the t ratio of the slope coefficient being higher than 2, again indicating that x2 actually explains y when there is no x3 in the model. And when we regress y on x3, we see that the estimated slope coefficient has the value of the t-statistic of 13.29, which is again higher than 2, and again confirming, and again showing that individually x3 explains y. So when there is no x2 in the model, x3 is statistically significant and indicating that it does have an effect on y.